Hello, CS111 students. This is the problem set video for problem set 5, task 3 on musical scales. And just as a reminder, you do not have to watch these videos if you don't want to. These are just running through what is already present in the problem set description. Um, for task 3, it's also of note that you have a choice. You can do either task 3 or task 2 for problem set 5. You do not have to do both. Task 2 is based on Turtle graphics. Task 3 is audio based. And so we're back to this choice between are you going to do graphics or audio. Task 3 is about musical scales. Um, now, if you haven't done an audio task before, there is some reference material on how to use the audio module and stuff. Some of that is included in an earlier task. And I also have included some of that here. So there's a music reference page that is linked from this problem set description, and you can check that out to sort of get familiar with things if you don't feel familiar with the synth.py module already. But it has some functions for creating musical notes, and it's probably a little bit more comfortable to use if you already know musical notation, but it shouldn't really be totally necessary either. Okay. The synth.py module has a notion of instrument. For this task, we'll always just be using keyboard as the instrument. So it's like a piano-like sound. The synth that we have is really cheesy. So it's not high quality or anything, but that's what we'll be using. And then in synth.py as well, when you're adding notes to the audio that you're sort of creating, you need a start time and a pitch value and a duration in addition to an instrument. And of course, the goal for this task is to add a certain series of notes that have the right start times and pitches and durations to make something that sounds nice. So I'm not going to go into all of the details here, but I just want to also mention pitch values are numbers, but those numbers have a sort of mysterious math behind them. The numbers are really just the frequency of vibrations that your ear will hear when you play that pitch. But in music, the way that those frequencies are organized, especially in the classical Western system, is not a simple system of linear pitch values. It's not like a note will be 10 and the next note will be 20 and the next note will be 30 and the next note will be 40. Instead, it's a multiplicative system. So we have given you functions in synth.py to manage this. Half step up and half step down will take a pitch value as an argument, and they will return a new value, which is one so-called half step up or down. It's like going one key up or down on the piano, including the black keys between the white keys. And as it explains here, a half step is 1/12 of what we call an octave. And an octave is actually a doubling of the frequency. So there's half step up, half step down functions. There are also step up and step down functions that take what we call a whole step. And so the different parts of this problem set on musical scales will be referencing whether you want to do whole steps or half steps up or down for different parts of it. Okay, there are 4 parts of this task, part A, B, C, D. Part A, you're going to create a fixed length scale using half steps. That will be exactly 1 octave of pitch. Part B is a variable length scale using whole steps. Part C is a variable length scale using whole steps where the notes are different lengths. So it has a kind of rhythm to it. And part D, you can create whatever you like. So a chance to get creative. There are some restrictions on how you have to do that. And remember that the theme this week is for loops. So we'll be using loops to produce these sequences of pitches because we won't know ahead of time all the factors that are relevant, so that we can't just say, oh, I'm just going to write these 12 lines of code that add these 12 notes the same way every time. So part A, you have to write the function half step scale, and there is a starter file. You can fill in the functions in that file. Half step scale takes 3 arguments. argument number 1, start at. What time in the track should the scale start? And this is cool because we can sort of overlap things if we tell them to start at points that are not just like, oh, this one should start at the end of that one. So start at determines when the first note is added to the track. Note length determines the length of each note. And starting pitch determines what pitch we start from. And the half-step scale function must return the end time of the last note that it adds to the track. So that if you wanted to, you could then take that and turn around and pass it as the start time to another half-step scale function call, perhaps. Or some other function that needed to know when to start playing notes. So when half-step scale is called, it must add exactly 13 notes to the current track. Each of them should be 1 half step above the previous, starting from the bass pitch. And so at the end of those 13 notes, you'll have taken 12 half steps in between them, and that last note will be 1 octave higher than the original note. The duration of each note will be the exact given note length. There's no randomization like we had in the past. And we have an example here of both what it looks like when you call a half-step scale and what the return value would be. In this case, if we say that each note should be 0.2 seconds long and it should start at the very beginning of the track times 0, then the end time of that scale would be 2.6 seconds, right? 13 times 0.2. If I play this, we'll be able to hear what it sounds like. Now, I'm not 100% sure if you can hear that on the video, but you can go to the website description and use this audio thing to play it yourself. And throughout the problem set description, there are a bunch more of those examples of what it should sound like. Okay, part B is a scale function. And the scale function gives us a little bit more control than half-step scale, which always adds 13 notes. It has a 4th parameter to control the number of notes in the scale. So same parameters as half-step scale of like, when are we starting? How long is each note? What is the frequency of the first note in the scale? But then also how many notes should be in the scale. However, scale doesn't just add notes going up like half-step scale did. Scale is going to add notes going up and back down. And if you've ever practiced a scale yourself on a musical instrument or heard somebody playing a practice scale, that's how scales are practiced in music, is by going up and then back down. So the start at parameter, again, specifies the start of the first note. The note length parameter specifies the duration of every note. The starting pitch specifies where is the scale starting, what's the pitch of the first note, and that will also be the pitch of the last note. We'll come right back down to that exact same pitch. The notes up parameter, that 4th parameter, specifies how many notes are in the ascending sequence of the scale. And that includes the first note itself and the top of the scale, the highest note in the scale. So after this many notes, each of them 1 step above using a step up, 1 step above the last pitch, there should be a complementary sequence of notes stepping back down to the original pitch. And if you think about that structure, let's say that there are 3 notes going up, I would have note A, note B, note C. Then I would step down, note B, note C again. So the part of the scale that goes down has 1 fewer note than the part of the scale that's going up. Okay. Like half-step scale, scale returns the end time of the last note that it adds. For the same purpose of somebody might want to play another scale right after that, well, they would have that information to tell that other scale where to start. So, as I mentioned, both the starting note and the highest note in the scale are included in notes up. And you can assume that notes up will always be an integer that's greater than or equal to 1 note. If the notes up is just 1, then the scale is just 1 note at that pitch. There's nowhere to go up, there's nowhere to come down. If it's 2, right, it'll be 3 notes. It'll be down, 1 step up, and then back down 1 step. There are other examples given here, including examples that use different pitch values, but I'm not going to go into all the details. You can read them in the problem set description. There are examples of what that will sound like. I'm not going to play them. You can play them for yourself. Okay, part C, uneven scale. This does the exact same thing that scale does. It takes the exact same parameters, has the exact same return value, but there is one difference. Instead of the notes all having the same duration, every other note in the sequence uses half of the given duration instead of the whole duration. So we still have a note length parameter, and half of the notes about are that length, but the other half of the notes are shorter, are just half as long. And the rule is that the top note of the scale is always a long note. So depending on whether the number of notes going up is even or odd, the first note of the scale might be short or it might be long. The top note is always long, and then sort of going down on either side from that, every other note is short, long, short, long, short, long. Again, we have some description of that in the text that you can sort of look and read over to make sure you really understand how it's supposed to work. And we have some examples of what that will sound like. Again, I'm not going to play them here because I don't think the sound quality will be good in the video, but you can play them for yourself. Part D, my scales. Having done uneven scales and half step up, you're basically done. You have one more task, which hopefully should be a little bit fun. The requirements are super simple. It's a function. It must take exactly one parameter, which will be a number, floating point, specifying the start time. So when is the scale going to add its first note? You must use a loop. You can use any kind of loop, a for loop or a while loop, but you must use a loop. And you must call at least one of either scale or uneven scale. Half-step scale not included, has to be scale or an even scale. And at least one of those function calls must be placed inside of the loop that you're using. In other words, you're going to have a loop that's going to add multiple scales to the current track. As long as you meet those three requirements, you can make your function as simple or as complicated as you like. It does not have to return the end time of the last note it adds, but it can do that if you wish. There's no requirement or testing of the return value of MyScale. So this is really a function where you get to do whatever you want. There's just some requirements about how you write it. And we encourage you to have fun with it. There are two different examples of what that might sound like here. And that's it for this task. The one other thing I want to point out real quick that I probably should have gone through earlier, in the scales part of the task, there's an example here where we call scale with 1.5, 0.2, E4, 4 as the parameters. Note that E4 is a value defined in the synth.py module that represents a pitch value. If you play this example, and again, I'm not going to play it because I don't think the sound will come through to you in the video, but if you play this example, you'll note that it starts with some silence, and you might wonder, why does it start with silence? Why doesn't the scale start immediately? That's because of this first parameter, right, which is telling it to start 1.5 seconds into the track. Okay, that is my problem set video for problem set 5, task 3 on musical scales. And remember that you have a choice between this task and the turtle-based concentric circles task. You can do either one. They both have the same themes of loops that are controlling some kind of either audio or graphical output.